One of the things I've learned about after many years of reporting on the energy transition is that energy is a technology. We're talking wind, solar, batteries, for example, and energy is a commodity, coal, oil, and gas. Those two things are fundamentally different. And one of the people who's helped me understand that is Mike Andrade. He's the CEO of Morgan, Toronto-based Morgan Solar. He's an engineer with over 30 years experience in electronics. So I'm going to talk to him about this fundamental question that we still need to understand better. So welcome to the interview, Mike.
Yeah, pleasure to be here.
Well, let's start with the big question. What's the difference between energy as a technology and energy as a commodity?
I think the fundamental difference, and it's not just about energy, as soon as you get electronics infiltrating something like we are now with batteries and solar in particular, the characteristics of competition and innovation change to look more like the underlying technology of the electronics that are in it. So I guess I view the question a bit different as whether it's a technology or not. It is now being driven like it is a technology because the cost curves and performance curves are based on electronics rather than extraction and ore reduction and things like that the past system was about. It's a disruption of the underlying competition based on the technology of electronics.
And I guess one of the fundamental differences is we're talking about energy as a technology is primarily electricity, whereas coal and gas can be burnt to generate electricity, but petroleum not so much. It basically they all get combusted to do whatever work the energy is intended to do. Mm-hmm. So let's talk about some of those technologies and Wright's law or learning curves. This is something that is a fundamental difference between the two approaches. What is Wright's law?
Yeah, I mean, Wright's law fundamentally is basically kind of economies of scale that you get more costs down based on increasing volumes. And in solar, it's, they call it Swanson's law. People are familiar with Moore's law and the things like that. I think that the fundamental difference between a technology-driven, disruption like we're seeing is there's a numerator and a denominator in the dollars per something. So if we're saying a dollars per kilowatt or whatever. And so the dollars part, the numerator, is worked on by Wright's law, Swanson's law, whatever, about, hey, we build more of these things, we get better at and cheaper at building them. The important thing is that then when you combine the bottom where you have some semiconductor-like physics or what have you, most famously with Moore's law, but it happens here too, where batteries get better and solar panels get better. So that dollars is the Moore's law, the Wright's law, that sort of. The bottom is more like the Moore's law of, hey, and for that dollar, I get more. And so to me, the bigger difference is oil sands can do better on the top line, get more efficient as an example. But nothing except for electronics works on that numerator through economies of scale and the denominator through physics in a way that's very, very powerful, frankly, unbeatable.
Yeah, I maybe should get a little background on Wright's law. I think it was Jim Wright, who was an engineer with Lockheed McConnell Douglas in the U.S. I think that's who it was. Anyway, he in 1936 he figured out that every time they doubled the production of airplanes, labor costs fell by 15%. Yeah. And so he worked this into a law, and other scholars have then gone on and further developed it. And I think the principle holds now that generally in any industry, if when you double production of something, solar panels, wind turbines, batteries, that you'll get a reduction in costs of 15 to 25% overall. And that's one of the reasons why we've seen, solar and wind, they've had this over the last 13, 14 years, we've had this cost curve where it started out here and then just went, and now we're talking about $1,000, say, a megawatt hour. Now we're talking about $25 a megawatt hour in the case of solar. And what that means is, as we produce, like as solar gets deployed more around the world, those costs will continue to drop. That's not the case with oil and gas, for instance.
Yeah, and Markham, I think people tend to understand the economies of scale, and that's why I think I focus on recognizing that top and bottom of it, because whenever someone refers to whatever, $1,000 per something or $100 per something, and they just attribute that to, hey, it's coming down in cost, they do think maybe there's a limit on that. The point is that when you can also say, and for that dollar, I get more, that's the exponential effect that we're seeing with solar. That's why the costs have really dropped. It's not just the panel cost manufacturing has dropped. It's that what you get for your manufacturing has gone up a lot as well. And that's particularly happening now with EVs and batteries too. That is, you're right. That is the fundamental difference, is this ability to have exponential performance improvement from both cost reduction and performance improvement. You just don't get from combustible fossil fuels with mechanical rotating things and all that. Steel is steel and fabrication is fabrication. You don't get those sort of effects with the current economic system and energy system.
So let's use an example to explore the point that you just made, Mike. Let's take electric vehicles and batteries. Now, batteries have followed essentially the same cost curve that wind and solar followed, and now I think the average in the last couple of years has been about $137 a kilowatt hour for a battery pack in an EV. But I've talked to battery scientists who say that that's going down to like $40 a decade from now because of those cost curves are going to continue. But at the same time, the energy density of those batteries is rising an average of 7% a year. So I think that's what you're talking about is, the costs are coming down as we ramp up production, but the batteries themselves are getting better. They're getting safer. Range in electric vehicles is increasing. Have I got that correct?
You do. And I just, I think people oftentimes talks about cost curves and they mix that numerator and denominator. I'm sure when people are saying they're coming down 40%, they're taking in count, hey, gigafactories are getting better and energy density is better. That numerator denominator thing, that's what's driving the bigger number.
Now, let's talk about electronic supply chains, because this is a point that you make all the time. And in fact, you've spent most of your career working in electronic supply chains. What's the significance of that?
Yeah, I mean, this is my job, from Celestica, was to find the next thing where commoditized electronics were going to disrupt industries. And it's basically, as soon as you introduce electronics, be it a plane or a car or whatever, all of a sudden the competitive advantage associated with building that thing starts to accrue to the people who actually have more electronics expertise. And usually how that manifests itself is that people are able to work that performance curve. They say, okay, I've got better drive control systems or what have you, and they're cheaper and they do better. Great. Then they're standardized electronics. So I can build them at the high scale to get those sort of curves that you talked about. They're not some customized bespoke thing. Then you can move them to global supply chains, both from the componentry, but as well as the manufacturing. And then once you've done that, you're opening yourself up to innovation, not just from what you can invent, but now you've outsourced the innovation because you have this entire supply chain working on improving the componentry that goes into it and the manufacturing of it that goes into it. So it just transforms itself to where you thought you were building, a washing machine or a car or a plane. And, the cars still have four wheels, but all the innovations driven by electronics. Washing machine still washes clothes, but all the features are driven by the electronics. And that innovation is happening because the componentry is being worked on by a fleet of people in the world and being manufactured with a fleet of people in the world, all bringing cost and innovation to your product that, was originally a washing machine or a car or a plane.
Right. It seems like, I've heard it described as, the vehicle now, the body of the vehicle and the tires and the steering mechanism, all of that is basically a commodity.
Yeah.
Everybody can do it. They've been doing it for decades, but it's all of the electronics around the battery, the power electronic systems, even the simple things like wiring.
Yeah.
Getting the wire, the wire. I read today that Tesla is for its electronics that run the car, it's moving from 12 volts to 48 volts, for example, which is much more efficient and smaller wires and then lighter weight. And those kinds of innovations, they're little things that you don't see, but they make such a big difference in the performance and the cost of the energy technology we're talking about.
Yep. I mean, you're seeing this now even in a tragic way in things like the conflict in the Ukraine, and where a lot of the innovation is these drones and things like that, right? And so what's it like? A drone is replacing a plane in things. How is that happening? Well, it still has to deal with aerodynamics and all that sort of stuff, which it's very complex. Let's not underplay building a car. These things are complex. The point is, it's not about the complexity or the difficulty. And we get into these arguments about, is the oil sands innovative? Of course it is. I'm an engineer. I'm a mechanical engineer. This stuff is not easy to do, that mechanical stuff. The point that's different is the innovation, that's a step function innovation, does not come from just being a better mechanical engineer anymore. It's like these UAVs exist because they have computing power on board, they have video on board, there's a GPS system, they communicate wirelessly. All of those things are consumer electronics, where all of the innovation has come from this extended supply chain put together in a clever way, and boom, you've got something different. So yes, it's a plane. Yes, it flies because it conforms to aerodynamic principles, but it is completely different. And the difference is the electronic supply chain and the electronics incorporated into it.
So, Mike, looking ahead over the next 5 or 10 years, as we move to this energy as a technology model, what do you expect in terms of, how fast the new technology, well, basically electricity generated by various forms of technology, and then the demand devices that use them, like electric vehicles and so on. How much is that going to accelerate from your point of view?
Yeah, I think you're bringing up another point too, is that there's just an inherent efficiency in electronics. So we talked about the electronics and the pace and the innovation and all that, but of course, as you also say, you're losing the conversion losses that you have associated about, combusting things and turning them into mechanical energy, which is very inefficient relative to kind of electrical systems. So the first thing that's going to happen is the projection that we need so much power is you don't need as much power, because people talk primary energy as opposed to moving energy. So it's going to move faster than people think, because you don't need to replace your entire energy system, because you're going to have a more efficient things. The second thing is, I think the exponential curve of performance improvement is we're just at the early stages. So that's going to rapidly go. I think the restraining factors, though, are regulatory, consumer, all of the sort of things that hold back change in general. I think that's going to be the rate limiting step. If you were to ask me from a technology standpoint, are we ready to transition? I'd say yes. I'd say the technologies are here today and are cheaper: solar, battery, EVs, heat pumps, etc. We could do it today, and we could scale them today, because it's not like, wow, we have to create new technologies and new innovations, new factories. These are just add dollars, build another factory, scale it, get the cost effects, you say, and rinse and repeat. We could do that today if we wanted. So the rate limiting step is not the technologies, the ability to manufacture, the materials, or anything like that, with all the noise you hear. It's going to be regulatory, consumer, just acceptance to change. And it's going to be fought by the incumbents every single step of the way. The utilities and the oil and gas industry are going to fight this rearguard action to slow it down. I think that's the rate limiting step.
Let's wrap up this conversation with this question. I would have to say I agree with you. And one of the things that North Americans are just beginning to understand, but I think given your years in the industry, you understand better than most of us, and that is the head start that China has got on the rest of us in these areas. And so as we make this transition over to electricity as the energy source, and all of the new technologies we need to take advantage of that, China's been doing this for 15 or 20 years. Yeah. And not only do they have the industry, not only do they have the supply chains, but they also have a culture that's very different to us. I mean, I interviewed somebody from China about their approach to electric vehicles, and they like their electric vehicle to be like a rolling iPhone. Yeah, where everything's interconnected, and they're basically their life is lived on the phone, and they see their vehicle as an extension of that. Where North America, we're miles away from anything like that, assuming we wanted it. And so, if the soft side of this is giving us a competitive disadvantage, how do we address that?
Yeah, I mean, I was part of the group in the late 90s that transferred electronics factories from North America to China. And that was for cost reasons and all that. But there were always technology sharing agreements. So for a long way back, the Chinese had looked at Taiwan and looked at Hong Kong and places like that and said, this is an area that we can get into because the robotics to assemble the circuit boards and all that were relative. You could buy them. And so they could put them in factories where most of the intellectual property was, and then just bring tons of low cost labor into the factories. And so this was from a long way back. They'd identified that this was a technology that they could get on board with. And then as I think they started thinking about, okay, what other industries could we get into? They tried to get into automotive, but what they were running into is the headroom about making transmissions and making engines and all that stuff, the mechanical energy, that's hard. And so we don't have a competitive advantage there. So I think as it started to form that maybe electronic vehicles were a way of the future, they started to combine that electronics capability, which by the way included huge amounts of battery capability because the lithium ion batteries were in your laptops, your phones and all that they were building. And they said, this is a convergence of two things we're really good at. And it eliminates the moat of mechanical precision manufacturing that we are not good at. And so this is an area we can dominate. Oh, by the way, people are still buying cars, so we can drive that with our own market. So we could get market demand as well as supply capability. And then we're going to do what Japan did, with the Honda Civic and the like. We're going to build it for our own purposes, and then we're going to become an exporting powerhouse. And then they did the same thing with solars. They said, we don't have a lot of oil and gas. We don't have sufficient, but the energy of the future is going to be more like electrical, solar. And once again, the solar supply chain is something that they are good at, high volume electronics sort of manufacturing with the raw materials that they can get. And so you look at all of the areas of this, they said, moving from something that I have a weakness at to now something I have a strength at, creating a moat against my competitors that I can use both my supply side manufacturing expertise, but my demand side to pull this forward. Very long view of that. Now, is it insurmountable? No, it is not, because all of those technologies were given to them by the West. But I tell you, it'll be a tough putt for us because we have lost in that from the 2000s till now. We probably lost in Canada 90% of our electronics manufacturing and 90% of our solar manufacturing. And there aren't a lot of people, unfortunately, with me who are old and had this experience that actually knew how to do that stuff. So we are going to have to recommit to actually building some stuff here, getting the next generation of people to do that, and recognizing that this is the energy of the future, that we can't rely upon, oil and gas and the things that we've been good at, automotive manufacturing, mechanical things. We know how to do it. We don't know how to do it at scale. And there isn't a generation of this expertise anymore. That's going to be the challenge for us. So I'd say it's insurmountable to catch up to them probably in total scale, but it's not insurmountable for us to have a meaningful manufacturing capacity in here to make sure that we are not completely dependent upon them. That's the bigger danger to me, is that our new energy system and automotive system is completely dependent upon China. I think that would be a really bad thing.
Well, Mike, thank you very much for your insights. Really appreciate it.
Yeah, appreciate the time as always.